So yesterday we had seen the difference between voltage follower and emitter follower, and out of these two, which one do you think is more beneficial? Is it voltage follower or emitter follower? Like, which one is suiting the needs of op-amp? Is it voltage follower or emitter follower? So it is voltage follower, right? So it is as good as an op-amp. So this is a concept that we use in op-amp. And we also looked into a few examples, right, as to how the voltage follower configuration is taken, and without voltage follower configuration, and we saw a few formulas as well, right? So today we will focus on non-inverting amplifiers, right? So as you can see in the circuit here, okay, so you can understand that it is in the non-inverting configuration, right? So you can see that it is connected to the non-inverting terminal, and then we have the internal resistance Rs, and then the supply voltage, and then we have Zi, okay, Zi here, which is the input impedance. Okay, fine. Then we have plus VCC and minus VE, R1. R1 is here, so we have taken R2, R3, and the current that is here is the I2 current and VI. Fine. So the same thing comes here, okay, because this potential, okay, whatever the potential that you see here is going to be whatever potential that you see here, okay, will try to be replicated at this point as well. So here you can see that one point is connected and the other point is connected to the ground. So here also I should be getting the same voltage potential, which is VI. Okay, fine. So we know that the voltage gain of a non-inverting amplifier. Now please take down this formula. As yesterday I was mentioning the importance of taking down the formula and noting down in one place so that it becomes easy for you to look into them before your examinations, right? So we have the formula ACL is equal to R2 plus R3 divided by R3. Okay, so ACL is equal to R2 plus R3 divided by R3. So what is this R2 plus R3? This is these two resistors are forming what type of configuration? Students, R2 and R3 is forming what type of configuration?
Voltage divider.
Very good. So it's acting like a voltage divider. Good. So so I will be considering just a moment. Yeah, so I will be considering these two resistors here, okay, because ACL, my closed loop, okay, closed loop from the output to the input, and the gain is very much dependent on R2 and R3 divided by R3. Fine. As always with the bipolar op-amp, design commences by selecting the voltage divider current, which is I2. Okay, so this I2 is what we are going to select. Okay, this I2 is what we're going to select. So current I2 very much larger than the maximum input bias current. So IB is nothing but input bias current. So can someone tell me, okay, how is current I2 very much larger than IB? So how is it that this I2 is larger than IB? Okay, so IB and I2. So concentrate on these two. How is it that these two, when I compare, okay, I2 is larger than IB? Can someone give me an explanation for that? If you have understood the concepts that we have gone through so far, I think you should be able to tell me that answer. What is the property of an op-amp? It has high input impedance or low input impedance? High input impedance, right?
Yes, sir.
Yeah. So which means because of this high input impedance, now we are trying to block currents, isn't it? So which means this IB is going to be very less compared to the I2 which is getting generated, right? So which means I2 is larger, okay? I2 is larger than IB. Fine. So we have seen this here that I2 is very much larger than the maximum input bias current. Fine. For a bi-FET, okay, bi-FET op-amp, the largest value resistor is first selected as 1 mega ohms. So generally what we do is we try to keep the maximum value, see, I'll tell you, it's kind of trial and error method. So we try to use starting with 1 mega ohms, and then slightly then we increase it to larger values. So initially we just start off with 1 mega ohms. In each case, voltage divider resistor values are determined using the input Vi and I2. Okay, so the value of these resistors, okay, how much should be R2 and how much should be R3, are all decided based on how much of input voltage and how much of current that is passing through, right? So I will keep Vi, I2, R2, R3. So all these are kept in mind, and then slightly either I increase the resistances or decrease the resistances based on how much of currents that needs to be generated. Okay, determined using Vi and I2, because VR3, okay, VR3, the voltage across the resistance R3 is also equal to Vi. Okay, so that's because whatever the voltages are here at this non-inverting terminal is tried to be replicated here at the inverting terminal. So because of which you have the same potential that is coming through. So Vi will also be the same here, and ground is common. Fine. So we have R3 is equal to Vi divided by, okay, it's just V is equal to IR. So I have voltage as Vi and current as I2. So the output voltage across, okay, is going to be R2 plus R3. Okay, so the output voltage will be across R2 and R3. So if I add them both, R2 plus R3, okay, so that will that is equal to, okay, your output divided by the current I2. So that's why this is called voltage divider. Okay, these resistances are called voltage divider because it is trying to divide, okay, between R2 and R3 to equalize IBR. IB is nothing but bias current. Okay, so to equalize the IBR voltage drops at the op-amp inputs, R1 is calculated. So if I want to think of how much of R1 that I need, anyway IB is going to be very less. So how am I going to configure this R1? Okay, so R1 is equal to R2 in parallel with R3. Okay, so please make a note of all these formulas, okay, because we will be using them in problems. We will be solving 1 or 2 problems today, and we will be designing an op-amp. Okay, so when I say designing the op-amp, It means that we will be designing or deciding as to what is going to be the values of R and what is going to be the values of I. Okay. So based on what is available and what is to be found. Okay. So if in case we do not have values for them, we assume the values taken from the data sheet. Okay. Right. So R1 is taken as R2 parallel with R3. If R1 is not very much larger than the source resistance, okay, which is Rs, then R1 should be determined from Rs plus R1 is equal to R2 plus R3. Now this is an important point here and you need to make note of this. Okay, if and only if there's a case here, if and only if R1 is not very much larger than the source resistance. So which means in that scenario, my source resistance is higher than R1. So let's say R1 is say 5 ohms. Okay, I'm just giving you some numbers. Say 5 ohms, and then your RS, say it is 10 ohms. So in that case, what you have to do, you just cannot consider R1 because this is very small. So instead, what you should do, you should consider both R1 and Rs. Okay, so both should be considered, and then these two should be in parallel with R2 and R3. Okay, so if in case R1 is larger than Rs, then I can neglect Rs, take only R1. R1 will be parallel with R2 and R3. So I hope these concepts are clear. Okay, so number one, we need to know what is ACL. Okay, and then we need to know what is how R3 is taken, and then how R2 plus R3. Okay, then how R1 is decided, and another case for R1. Okay, so basically, if we if I have to tell you the things, the most differentiating formulas, then it's going to be 1. Okay, then R3, yeah, R3 also is important. And this is important, and this one, yeah. So these 4 are going to be important for you all, and this is just another sub case of the previous formula. So I hope you have understood the concept of these amplifiers, non-inverting amplifiers. So basically here, whatever input is there, the same kind of output we are going to get. If it's in the positive cycle, the output is also going to be in the positive cycle. So there is not going to be any inversion. So that's why the term inverting, non-inverting amplifier is used. Okay, non-inverting amplifier is used. Right. So can I move on to the next concept? Yes. Based on these, we will try to solve some problems. Okay.
Yes, sir.
I hope these formulas are taken down. Yes. Have you all taken down the formula?
Yes, sir.
Okay. Fine. Now let us solve one example. I have 2 examples in mind, and we will start off with the first one. Okay, using 741 op-amp design. Okay, so the reason why we are giving this 741 op-amp is so that you guys will refer to 741's data sheet. Okay, so that's why it's always specified 741. Using 741 op-amp, design a non-inverting amplifier. So when I say design, as I mentioned previously, we are going to decide as to how much of resistors and what currents are getting generated, and to the same circuit that we saw in the previous slide. So design a non-inverting amplifier to have a voltage gain of approximately 66. So we have something given here which is about 66. The signal amplitude is to be about 15 millivolts. So when I say signal amplitude, it means the input signal here is going to be 15 millivolts, right? Okay, so we have some clues here. Okay, so let us just highlight those clues, and based on that, we will start working. So first of all, the clue is 741 op amp, and in that, they're telling us that the circuit is going to be in the non-amplifying mode. Okay, non-inverting amplifying mode. And the next thing is, they're giving us the voltage gain, which is about 66. And then they're telling us the amplitude is about 15 millivolts. So these are the data that is actually given to us. So based on this, we will try to build up, and we'll try to find out what needs to be found. So we know that for 741, okay, IB max is about 500 nanoamps. I don't know if you can remember when we were doing this bias currents, right? Input bias currents, we had seen this number. How many of you can recall 500 nanoamps? Can you recall when we were doing this input bias current, right? We were doing this biasing. So there, we saw these values. Can you remember? Yes, no? Okay, so let me show you. Yeah. So here you can see the input bias current, okay, that is IB is 500, and the unit is nanoamps. So 500 nanoamps we are taking, right? Is that clear? Now can you recall? So maximum we are taking, okay, maximum input bias current. Fine. Okay. So getting back to the problem, we have seen that the input bias current is 500 nanoamps. So now we have to select I2. Okay, I2 is the previously which was towards the output side. So we will make this I2. Now remember, I told you I2 is much larger than IB max, right? So we will take it 100 times the value. Okay, 100 times the value of IB max. So when I multiply, students, again, I need your help. Please verify if these values are right. Okay, so multiply 100 with 500 nanoamps and just check if we are getting 50 microamps. So I think with this we are clear, isn't it, with IB max? Can I have some responses?
Yes, sir, same value.
Yeah. So which means 50 microamps is also correct?
Yes, sir.
Okay, fine. So the reason why we are doing this is because I2 is much larger than IB, right? So we take it as 100 times and it becomes 50 microamps. Fine. Now we have the formula for R3. Where was R3? R3 was at the bottom, right? And VI, why we are taking VI? It's because it is as good as the input voltage divided by I2, right? So we know that we have about 15 milliamps, 15 millivolts, sorry, for the input voltage, right? So I am taking it from there. Okay, so I'm taking it from there, and this I2 value is again taken from here, right? So calculate and tell me if it's correct. R3.
Yes, sir, correct one.
Correct only. So we are getting about 300. And since we are talking of resistance, so the unit is going to be ohms, right? So now we have the value of IB, we have the value of I2, we have the value of R3. Now, since I have R3, I have VI, I know I2. So now it's going to be easy for me to calculate which resistance, which is pending for my design.
R2.
R2 is pending, very good, and R1 is pending, right? So we will calculate that as well. So there's a small, information given here that use a 270 ohm standard value resistor for R3. So instead of 300, so we don't get 300. So what we'll do is we will use a standard value, which is available in the market, which is 270. And this will give a level of I2 slightly greater than 50. Now, if I'm reducing this resistance, right? So what is going to happen to I2? Obviously, it's going to be more than 50 microamps. Why is it so? Why is it so? You understood what my question is, students?
Can you repeat the question once?
Now, instead of this 300 ohms, okay, if I replace this 300 with a 270 ohms, okay, I'm replacing instead of 300, I'm replacing with the 270 ohms. So by doing that, by replacing this with the 270 ohms, my resistance goes down, isn't it? My resistance
Yes, sir.
goes down. Since this resistance goes down, what is going to happen to I2?
It'll increase.
Very good. So I2 will surely increase. So which means we are going to get a slightly higher value than 50 microamps, right? So this was calculated, we calculated 50 microamps and resistance was 300. But we will not be putting 300. I'll be putting a lesser resistance. So because of which I'm not going to expect the same calculated 50 microamps, but then it's going to be a little higher. Okay. Right. So moving on. Okay. So now, you are, taking an op-amp here like this, and you are deciding as to what are going to be the resistances. Okay, so R3, I'm going to put it as 270. Now I need to find out R2. Of course, these are put up, after completing the problem. So now let us come to I2. What is I2? I2, which was here, isn't it? So I2, I know the value of R3, I know the value of VI. So which means VI was 15 and R3 was 270. So previously, what was the calculated value for I2?
50.
Yeah. So slightly you can see that, it has been increased. Okay. So just cross check if this value is correct. 15 milli.
Yes, that's correct.
Divided by 270.
We are getting 55.555.
Yeah, so 0.6 we can take, right, approximately. So next we will take V0, okay, the output voltage. So we know that, output voltage is, gain into input voltage, isn't it? So we have seen this exclusively in many of our studies before, right? V0 is nothing but ACL, the gain into input voltage. Now, how did we get the 66? How did we get the 66? Students, you're with me? Are you all with me? How did we get 66? Yeah, can I have a response? Kevin, how did we get 66? Manoj, Mansoor, Vishwas, how did we get 66? Yeah, Bhumika, go on, go on.
Sir, it is mentioned in the question.
Correct. So ACL was already given, right? Approximately we need that, that ACL should be 66. So we are taking, thank you, Bhumik. So we are taking that value here, 66. And the input voltage, as we know that it is 15 millivolts. So are we getting 990 millivolts? Just check. Can one of you confirm it for me?
Yes, sir.
Okay, thank you. So 990 millivolts is going to be my output voltage, right? Okay, so we know that R2 plus R3, this R2 plus R3 is equal to whatever is the output voltage divided by the current that is coming through. So we have calculated 990, I2 is the new updated I2 is 55.6 because of the updated resistor value, because 270 we get it as a standard value, we don't get 300 ohms. Of course, we can put it in series and do those things, but we do not want to complicate things. So what we will do is, plus or minus 20-30 ohms here and there is fine, because it's not in the range of kilo, right? So R2 plus R3, this value. So are we getting 17.8 kilo?
Yes, sir.
Yeah, fine. So 17.8 kilo ohms. So this is a combination of both R2 and R3. Now we know that, R2 is equal to, we had seen this formula, R2 plus R3 minus R3. So it is as good as plus and minus, right? So plus and minus goes off. Ultimately, we are remaining with R2. So, the combination is 17.8 minus 270. So how much are we getting? Are we getting this 17.53? Now remember, this is in kilo ohms. This is only ohms. Yes, are we getting R2 in this value?
Yes, sir.
Okay, good. So here again, 17.53, I don't, get this resistor. So what I will do, I will use a standard 18 kilo ohms, right? Now, since this is changed, okay, so, slightly there is going to be change in the levels of currents and voltages, right? 18 kilo ohm standard value resistor to give ACL greater than 66. Alternatively, use 15 kilo ohms in series with 2.7. This is also fine, right? So this will give us 15, 16, 17. 17.7 is it's going to give. We can either use this 17.7, okay, or we can use 18 kilo ohms, right? So you have two options. As I mentioned previously, you can put it in series, and yeah. So R1, okay, now the only thing pending is we have to calculate what is R1. So R1 is pending, right? So R1, we know that, it is in parallel, okay, with R2 and R3. So I have 18K and 270K, 270 ohms, right? So we are going to get approximately about 270 ohms. Is it right? Is the value fine? $270 ohms. Yes or no? What's the formula? How do we get this R2 R3 in parallel? How do we calculate it? Students, you have studied network analysis, right?
Yes, sir.
So what's the value? What is the formula for R2 R3 in parallel combination?
1 by R2 plus 1 by R3. Whole inverse.
You can take that, or you can take R2 R3 divided by
R2 plus R3.
R2 plus R3. That also can be done. So I think if you calculate, we should be getting about 266, right? Yes or no? Are we getting 266?
Yes, sir.
Yeah. So what we will do is we will use a standard resistor. Okay. As mentioned previously, we will be using a 270 ohms. Okay. So here and there, slightly the values can change. So ultimately what you can do, you can just put all those values here, right? So R1 value is there, and you can put your R2 value, then R3 value. Okay. So this is how you design your amplifier. Okay. So we will see now with the other problem as to how we can enhance our learning. So is that clear, students, with the concepts discussed so far? Any doubts in this problem?
No, sir.
Okay. So now let's look into the next example. Okay, so here we have to redesign. Of course, this problem is just for your understanding. Okay, most probably we wouldn't be giving you problems as something which is not relating to 741. Okay, majoritarily we will be giving you problems based on 741 only. Okay, but you need to know the importance of how these resistors are all calculated based on the assumed values. Okay, fine. So we are now taking a different non-inverting amplifier. Okay, so instead of the same circuit, okay, we're using the same circuit. Instead of 741, okay, we are going to use LF 353. Of course, this data sheet is available. Okay, and based on that, we will be calculating the problem. So here also, you can first take what is given, right? So you need to design a non-inverting type of amplifier. Okay, so you know that it's going to be connected to the plus terminal, and you are going to use 753 LF353, sorry, by FET op-amp. Okay, and redesign means what? I need to find out the values of R1. I need to find out the values of R2. I need to find out the values of R3, right? And we will see as to how this goes. Fine. So based on the data sheet, okay, we have IB max, just like how I showed it is 500 nano. So here it's going to be about 200 pico. Okay. So IB max, and we'll be taking I2. I2 is something which comes here, right? So I2 is equal to 100 times IB max. So that's going to give us about 1 mega ohms. Okay, so this would result in very large resistor values. Therefore, so can you just calculate this 100 into 200 pico? How much do we get? how much are we getting I2 if it's 100 times IB max?
So 200 micro.
200 micro or 20 nano?
20 nano, sir.
Correct. 20 nano.
Yeah.
So
Yes.
20 nano you're going to get, and of course that is very much larger compared to the pico values. Fine. So we select the standard value. Remember, we were discussing that generally we will take R2 as 1 mega ohms. We start off with 1 mega ohms. So, and also we know that ACL. Now this is also another important formula, right? Please make note of it. You will be needing it. ACL is equal to R2 plus R3 divided by R3. Okay, right. And we have R3. Okay, R3 is equal to, so we are just remodifying this equation. Okay, we are just remodifying, and we are getting R2 divided by, we are just taking R3 common, right? Because I want to find out R3, right? So how do I take R3? If I take here, then it becomes 1 plus R2, right? So and then I invert it, right? So I do all those minor modifications, and finally I end up with R2 divided by ACL minus 1. Okay, so we know that R2 we have taken as 1 mega ohms, and ACL was already given to us as 66 minus 1. So please check and let me know if it is 15.4 kilo ohms. Can divide it by 65. Yes, how much are we getting? Are we getting this value?
Yes, sir.
Yeah, okay. So approximation is what we are going to do there, right? Okay. So this value is correct. So we will not be getting this 15.4. So we'll be using a standard 15 kilo ohms resistor. Okay. So ACL will slightly go greater than 66 because the resistor is going to be a little less. Okay. So the gains are going to be higher. So we know that R1 is equal to, in order to find out R1 is equal to R2 and R3 in parallel combination. So are we getting about 15 kilo ohms? Please check. 1 mega and 15 kilo.
Yes, sir.
Getting it, no? Right. So we have this value also to be right. So we can use a standard 15 kilo ohm resistor because we already have this value here. So with this we conclude our today's class. Okay, and we will be looking into few other configurations. Right now we have discussed this non-inverting, right? And we will be even looking into the inverting amplifier. Okay, inverting amplifier, then summing amplifiers and difference amplifiers in our upcoming classes. And also we will try to solve few more problems. Okay, I expect all of you to be a little more active and try and solve along with me so that we will be able to understand the concepts, right? So can we end the session today?
Yes, sir.